Yesterday we introduced this brand new concept called projectile motion. It involved an object flying through the air under the influence of only gravity. We call that a projectile, right? The object that flies through the air under the influence of just gravity. Here's one object that may be flying through the air. You know what? Actually, let's go back. Let's not make it a ball. Let's make it. He's all happy right now because he doesn't know he's going to run over a cliff. Let's make it our red-tailed buffalo again with our little pom-pom on the end of his tail. A red-tailed buffalo is about to run off the edge of this cliff. That red-tailed buffalo will become a projectile. What's the shape of that projectile called? We know it looks something like that, right? What's the shape of it called, Aiden? Good. It's called a parabola. If you haven't learned that in math class right now yet, when you go and learn it in math class, it will at least be familiar to you when you learn it in math class. It's called a parabola. And a parabola is described by the equation y is equal to ax squared plus bx plus c. Those of you who have learned about a parabola, you'll recognize that equation. Okay? In the end, we describe this situation by two equations. We have to break it up into the x components and the y components. The x component is always described by which equation? Has to be one particular equation because it involves one particular type of motion. Lewis, what is it? Good, constant velocity. And the only equation that we have that describes constant velocity is delta d over delta t. Now, there's v's all over the place here, right? For the x and for the y. VI's, VF's, v's, whatever. The x component, y component. This v is the constant v for the x component. You can't use it anywhere else. Okay, you can't transfer that number over to the y component. Can't make it VI, can't make it VF, so on. D, same thing. Displacement in the x direction, not the y direction. T is the only one that can go back and forth between x and y, because T can go back and forth between x and y because T's a scalar. You guys remember the equation? We got 5 equations that I could use for the y component, but one that I almost always want to try first because it's the one that's going to work 95 or better % of the time. Which equation do you want to try for the y component here? Yep. Good. Good. D is equal to VIT plus 1/2 AT squared. Let me show you something for those of you who have learned about parabolas in math class, okay? For those of you who haven't, don't worry about this little thing that I'm about to show you. Don't panic about it. It won't be on a test, okay? Not a physics test. It might be on a math test sometime. Take a look at this equation down here that describes the y component. D is equal to VIT plus 1/2 ET squared. What have you guys done with your parabola equation before? You guys remember finding the zeros? The zeros, in other words, the values of x. Do you guys remember how you did that? Well, y had to be 0, right? Right? Take a look at this equation down here that we describe the y component with. If we rearrange that, it looks like this. VIT plus 1/2 AT squared minus D. Let's rearrange it a little bit further. Let's say 0 is equal to 1/2 AT squared plus VIT, subtract delta D. Now I want you to compare those two equations. The equation that describes the parabola that you learned in math class, and now the equation that describes the motion of this object, the vertical motion of this object, this red-tailed buffalo that's just jumped off the edge of this cliff. 0, 0. AX squared 1/2 AT squared plus BX plus VIT plus C subtract delta D. What we're saying here is that the value of A is half the acceleration. The value of B is the initial velocity. And the value of C is negative delta D, negative of the displacement. Is it a coincidence that this equation that we described, the y component of this projectile motion, matches up with the equation that you guys used in math class to describe a parabola? Why would it be a coincidence? What's the shape of this path? It's a parabola, right? So of course The equation that you're going to use to describe it in physics is going to be the equation for the parabola. It just looks a little bit different than the form of it that you learned in math class. This is our equation for a parabola. D is equal to VIT plus 1/2 AT squared. It's the same thing. It's just a little bit more specific of a form. Okay, it's used specifically for displacement and so on, whereas this equation that you learn in math class is a more general form of a parabola. Does that make sense? Those of you who've learned about parabolas in math class? If you haven't learned about parabolas, that's still, like, you might see some similarities there. It's still not going to make a whole lot of sense to you right now, and that's okay. Okay, but I hope when you do learn about it in math class, you'll remember this a little bit and say, oh yeah, I remember the significance of parabolas and so on and so on and so on. Now or later, hopefully it'll make some sense to you. All right. So what do we do at this point? Solving this problem, you get two equations written down. Now we plug numbers in, and we try to solve for something. It doesn't matter what you solve for. Okay, if you're looking for v for the x component, great. If you can get it right away, fantastic. If you can't, that's okay. If you're looking for the displacement for the y component, in other words, the height of this cliff, again, plug numbers in. Get something. It doesn't matter if you get what you're looking for right away. Just get something. And then we'll worry about solving what we're actually looking for. The one thing that usually happens is this. Not always, but usually. Okay? Usually you end up solving for time first. Either time here or time over here. If you solve for time, Atlanta, usually you're going to use that time to plug into the other equation. Not always, but usually. So what usually ends up happening is you try one equation, you get a time, it's not what you're looking for, you plug it into the other equation to get what you're looking for. Does that make sense? All right, we did an example yesterday, and we left you with 3 practice problems yesterday. The second one, I know, presented people with a bit of a problem. I expected that. It's a good question. It's got a piece of data in there that's meant to throw you off. It's meant to trick you. And I know that it tricks some people. You know what? Honestly, if I was in grade 11, if I was your age, it probably would have tricked me too. Okay, it doesn't mean you're not smart. It doesn't mean you don't know what you're doing. Okay, it probably would have tricked me too if I was your age. Any other issues besides question number 2, though? Are we okay with 1 and 3? All of them? All 3 of them? Yeah. Okay, so number 1 says a coin rolls off a table with an initial horizontal speed of 30 centimeters per second. How far is it going to land if the table's height is 1.25 meters? You should always, as I called you up and checked your homework here today, some people said, I didn't draw a diagram, I just did it. And I marked it done because I could see that you worked on it and did it. But listen, you should always draw a diagram for these problems, always. Anytime you have a 2-dimensional interaction, you should always draw a picture. There's my picture. There's my coin going off the edge of the table. The height of the table is 1.25 meters. The initial velocity of that coin is 30 centimeters per second, or 0.30 meters per second. Let's go meters per second. Okay, in this question, you could actually get away with going centimeters per second, but usually you can't. So I want to avoid that. Let's convert it to meters per second. We want to find out how far from the base of the table it's going to land. I'm telling you right now, your final exam in Physics 20 will have about 25 multiple choice questions, and it's going to have about 10 more short answer questions like this. Question number 1, short answer question number 1 will be a projectile motion question. I'm telling you right now. Okay, question number 1 on your exam at the end of this course will be a projectile motion question. Everybody better know where to start it. Okay, you don't have to really know anything to know where to start this question. Draw your picture and then write down V is equal to delta D over delta T. Every single time. And D is equal to VIT plus 1/2 AT squared. Every single time. You're going to try that. If you don't write that down for question number 1 of your final exam, I'll be sad. It's the same every time. You know how you're going to start off question number 1 right now. You may not be able to finish it, but you better be able to start it. All right, let's plug some numbers in. Don't worry about what we're looking for. Let's just plug some numbers in and see what we can get. Do we know v for the x component? How much of the velocity at 0.30 meters per second is horizontal motion, is on the x-axis? How much of it? Yeah, 0.3, all of it, right? 0.30 meters per second. Do we know delta d for the x component? Is that 1.25 meters, a delta d? It is a delta d. Is it the delta d we want here? Ellie? No, that's the y component, right? The up and down. We're looking for the horizontal here, right? We don't know what delta d is. We also don't know what delta t is. Okay, that wasn't very helpful. That's okay. That's okay. That's normal. We see things like this all the time where we try something, doesn't quite work out. Try the other one. Delta d for the y component, Derek, is what? The up and down motion. Almost. We'll make it negative 1.25 because it's down. Vi for the y component is what? How much of that 0.3 meters per second is downwards or upwards? Good. So let's just cross that term off, right? 0 times whatever the time is still 0. 1/2 of the acceleration, which is negative 9.81, if we're on Earth, that is. Okay, you're going to get a question later today where I think you're on the moon. Okay, gravity's not going to be 9.81 on the moon, right? But on Earth, it's always 9.81. Half of negative 9.81 is negative 4.905. So let's say 1.25 divided by 4.905. Let's pull with the calculator and show you this. So remember, it's half of negative 9.81. Negative 1.25 divided by negative 4.905. 0.25. Then we square root that to get t. And we end up getting 0.5048 seconds. Okay, that's not what I'm looking for. It's not what I'm looking for, is it? What did I just tell you a minute ago? Usually happens. Usually you solve for a time, but usually it's not the time you want. Usually it's, you got to use that to put it into the other equation. So let's do that. Let's take that and plug it in over here. Let's replace delta t with 0.5048. Now we solve for d by taking that up by multiplying. And we end up getting 0.151 or 0.15 meters. How far does the coin go out? 15 centimeters, 0.15 meters. How many people got that one? Good. Good. Then you're well on your way to getting question number 1 on your final exam. Yeah. It did, yeah. But that initial speed of 0.3 was rolling off the table with a horizontal speed of 0.3, right? So that would be my horizontal velocity right here, right? 0.3 meters per second, not the vertical velocity. The vertical velocity, when it was launched, would be 0. A tenth of a second after that, it would be something. But in the equation, you're asked for the initial velocity there, not a tenth of a second later. All right, let's take a look at number 2 now. This one says an arrow is fired horizontally with a speed of 25 meters per second from the top of a 150-meter high cliff. Let's not take up so much space there. There we go. That's 150 meters. Here's my arrow. It's launched with a velocity of 25.0 meters per second. The time we're given this time is 2.50 seconds. We want to find out how far it will drop. We want to find out this number. How far it's going to drop in 2.5 seconds. It doesn't say it hits the ground, does it? How long does it take to hit the ground 150 meters down? I don't know. Maybe it does go all 150 meters down. Maybe it doesn't. Doesn't tell us. It just says the cliff is 150 meters high. How far down does it go? What equation are we going to use for x every time, including on question 1 in your final exam? Seth? Good. Seth's not going to get a 0 on his final exam. Seth already knows something for his final exam. Guaranteed, Seth, you don't have a 0 on the final exam if you remember that, okay? Something. Probably get a 1% or so. Then all you have to do is kind of work from there and get it up another 85 or so percent. V equals d over t. Good. What equation are we going to try for the y component? The one that almost always works. The one that you will try every time. Tony, which one are we going to use for the y? This one's a bit harder. Yeah, I know. If you have your data sheet in front of you, you'll get it, right? As long as you remember more or less which one it is, check your data sheet and you'll get it. VIT plus 1/2 AT squared. You don't need to memorize the equation. You just need to be able to know when you look in your data sheet which one to put there. All right, so let's plug some numbers in. V for the x component is 25. Delta D for the x component, don't know. Delta T is 2.5. Delta D for the x component ends up being 62.5 meters. Is that my answer? No. What have I just found? Okay. Total displacement. Can you be more specific? Distance? Be more specific. Found this distance, right? Or this displacement. How far it goes horizontally. Is that what I'm looking for? I want to know how far it drops, not how far it goes horizontally. You know what I've just done right there? Something that I didn't need to do. I will not use that number anywhere in the question. Listen, I'm sorry to tell you this. I've just wasted 30 seconds of your life. 30 seconds of your life that you're not getting back. I'm sorry about that. Listen, it's only 30 seconds, okay? The point that I want to make here is that this is the way we set up a problem. If you solve for something you don't need, so what? 30 seconds. Move on and solve for something you do need. If we follow the same strategy every time, we'll either get what we were looking for or we'll waste 30 seconds. No big deal. We're not going to get a wrong answer, though. That's not a wrong answer. It's just not the answer. Let's go to the y component. Delta D, it's not 150. We want to find out how far it falls. How far does it fall? I don't know. I don't know. That's what I'm trying to find. VI is 0 because it's launched horizontally. So delta D is 1/2 of negative 9.81 times 2.5 squared. 0.5 times negative 9.81 times 2.5 squared equals negative 30.7. That's my answer. The cliff was 150 meters tall or high, but the arrow only fell 30 meters because it only fell for 2 seconds, 2.5 seconds. Hey, by the way, they have an answer of positive 30.7. I got negative 30.7. What's the difference there? Like, how did I get my answer versus them getting their answer? Yeah. Yeah. I haven't really found the height, have I? What have I found? I haven't found the distance, sorry. They're asking you for the distance. I haven't found the distance. What have I found? The displacement. So what would the distance be? 30.7, right? You leave negative 30.7, I'll never mark that wrong. Okay, don't worry about that. Even though technically it's displacement, not distance. Got it? Who got that one? Good. Guys, in the end, look at what I ended up having to do. That's it. That's it. Mathematically, it's easy, right? It's just getting to that point. How many people did what I did first, the x component, and ended up solving for the displacement in the x direction? Like, who cares, right? Who cares? Tiny bit of extra work, no big deal. Okay, let's check number 3 now. What's the horizontal speed of an object if it lands 40 meters away from the base of a 100-meter high cliff? This is 100 meters. This is 40 meters away. And this is our object. Our happy buffalo, because he's not very smart. But this time, he's the green-tail buffalo, the lesser known of the mutant strain of the red-tailed buffaloes. The green-tailed buffalo runs off the edge at a certain speed. We don't know what that is. That's what we want to find. So what do? Every single time, X and Y. All right, who's going to get at least 1% on their final exam right now? Who knows which equation to put in here for the X component? Lewis knows. Lewis is going to get 1%. Good. I knew Lewis was going to get at least 1% before he even told me that. Now I know for sure. What about the Y component? Who's going to get the 2nd percent on the final exam? Good. You guys are so smart. Plug some numbers in here. V for the X component, we don't know. Delta D for the X component, we do know it's 40 meters. Not 100, it's 40. T, we don't know. Let's go over to the Y component. D, look, this green-tailed buffalo ends up down on the ground, 100 meters below where he started. Delta D would be negative 100. VI for the Y component would be 0. Look, we want to find the time again. Let's say negative 100 divided by negative 4.905. That's a half of 9.81. Let's square root that. 4.515. Remember what we said? We usually end up taking the time from one of them, putting it into the other. Do that math, works out to be 8.86 meters per second. What's the speed of this buffalo as he jumps off this 150-meter high cliff? 8.86 meters per second, horizontal motion. Okay. Who feels okay about this stuff? Who feels like if they were to write their final exam right now, they'd get question number 1? Good. Well, there is a little bit more to projectile motion, and you will be asked a little bit more than what we've shown you here, but it's a good start. Okay, have a look at this, everyone. The diagram that you see up on the board right now is essentially what we've been looking at for the last 2 days, right? It's an object, a green-tailed buffalo. It's running off the edge of a building, or the edge of, well, probably not a building, because a buffalo probably wouldn't be on the top of a building, but top of a cliff, okay, 20 meters down. Versus our red-tailed buffalo that's jumping. Do you know that the red-tailed buffaloes actually can jump pretty high? pretty high and pretty far. Okay, so this red-tailed buffalo is jumping up at an angle of, let's say, what angle do you want to use? What angle should we use here? Okay, 30 degrees, thank you. Let's use the angle of 30 degrees. I don't know why you guys always insist on using 30 degrees, but 30-degree angle here. It's jumping up at a speed of 10 meters per second. So kind of the same question, kind of different, obviously. Well, how do we tackle this one over here? X and Y components, right? We've done this half a dozen times. V equals delta D over delta T. And D is equal to VIT plus 1 half AT squared. Nothing new there. How do we tackle the one on the right-hand side? Oh, I'm waiting for somebody to give me the answer, the correct answer here, and impress me to no end here. How do we tackle the one on the right-hand side? Yes, you use some trigonometry. I was looking for 5 words, actually. I don't like funny angles. I got 30 degrees. I don't like it. So I got to use some trigonometry to get rid of that 30 degrees. Let's draw it off to the side up here. 30 degrees, 10 meters per second, x and y. We're going to say cosine 30 degrees is equal to x over 10. X is 8.66. And we'll say sine 30 degrees is equal to y over 10. Y is equal to 5. So I've got rid of my funny angle by using some trigonometry. Now I'm going to go to the exact same places I went to for the last question, x and y components. V equals delta D over delta T. D is equal to VIT plus 1 half AT squared. Your question on your final exam will be one of the 2 questions you see up on the board right now. Either something launched horizontally off the edge of a cliff or building, or something launched at an angle from ground level. In either case, you'll start it off with D over T and VIT plus 1 FET squared. If it's this problem, then you'll also get rid of that funny angle using some trigonometry. Okay, let's plug in some numbers here. Let's say we're solving, by the way, for this distance in both cases. How far the buffalo goes in both cases. What's V over here for the x component? Be 10. Delta D, we don't know. T, we don't know. What's delta D for the y component? Negative 20. Equals 0. Plus 1 half of negative 9.81 times t squared. We're going to solve for t here, plug it into the x component, solve for the displacement. We can do that. Let's come over here. What's v for the x component? Oh, who's going to give me this one? First time. What's v for the x component? Nope, not 10 meters per second. 8.66 meters per second. See that, guys? We don't like that funny angle. We don't like 10 meters per second at 30 degrees. So we got rid of it and said, well, it's the same thing as saying 8.66 horizontally and 5 up. We don't know what delta D is. We don't know what delta T is. So the first difference between these 2 problems is this. The horizontal velocity in the first problem is just the velocity you're given. In the second problem, it's a component of the velocity that you're given. That's the first difference. What's delta D for the y component? Look at this. Okay, ball's going up, or buffalo going up. What's the vertical displacement? Where does it end up vertically relative to where it started? Okay, 0. It lands on the ground. There's the second difference in these 2 problems. We've got the horizontal velocity is different, and the vertical displacement is different. In these problems, it's going to be the height of the building. In these problems, it's going to be 0. What's VI for the y component? Five meters per second. That's the third and final difference. Let's use yellow there. That's the third and final difference between these two problems. The x velocity is different. The velocity is different for the x velocity. The y displacement is different between these two problems, and the initial y velocity is different between these two problems. Once you get past that, it's just math. It's exactly the same thing. Okay, the math is a little bit trickier on the right-hand problem, though. How do you solve for t there? Somebody asked, I think it was Haley a few minutes ago, could you ever have VI for the y component that wasn't 0? Here we go. How do you solve for t there? That's ugly. Ugly. Okay? You don't actually have to use the quadratic equation here. No, you can simplify this. What's 0 divided by t? 0. What's t divided by t? 1. What's t squared divided by t? T. Am I allowed to divide everything by t? I can divide everything by whatever I want as long as I divide everything by the same thing. Cancels out. I'm left with 0 is equal to 5 plus half of negative 9.81 or subtract 4.905 times t. Well, that's a lot easier now. Take a t out of every term. That's what you're left with. Take that over to the other side by adding. And let's solve for t. .0194, which we turn around and plug into here, the same way as we did when we solved for time over here. Harder? Yeah, a little bit. What makes it harder? This up here. Okay, once you get that stuff, then the problem is just about the same as the problems that you were working on yesterday and earlier today. All right, a real example here now, guys. This one on page 109 says, baseball players often practice their swing in a batting cage in which a pitching machine delivers the ball. The baseball is launched with an initial velocity of 22 meters per second at 30 degrees, and the player hits it at the same height from which it was launched. For how long is the baseball in the air on its way to the batter? So the ball is being launched from this pitching machine at 22 meters per second at an angle of 30 degrees. Now, it's not from ground level, but we know that it's ending up at the same level that it started. So whether it's ground level or bat height or whatever, it doesn't matter if it ends up at the same height that it started. That's the baseball's motion right there. What's the shape of that path of the baseball called, by the way? Yeah, good, parabola. Okay, that's all we know. What we do want to know now is, what we want to solve for is the time that it's in the air for. In football, we call it the hang time, right? Who knows what to do first here above everything else? Yeah, we don't like funny angles. So let's get rid of that 30 degrees. 30 degrees, 22 meters per second. This is x, this is y. Let's say cosine 30 degrees is equal to x over 22. Let's say sine 30 degrees is equal to opposite over hypotenuse. Now we got rid of the funny angle. We could, if we wanted to, replace that with just two vectors like that. X and Y. D over T. And VIT plus 1 FAT squared. Can you tell me what V is for the X component? Lana, what's V for the X component there? Yes, good. 19.053. We don't know what D is. We don't know what T is. Okay, wasn't helpful. That's okay. No worries. D for the Y component. Jordan, what's D for the Y component? No. Delta D, displacement for the Y component. The final position minus the initial position, Derek. Good. 0. It ends up in the same place as it started, right? Vertically it does. VI for the Y component is 11. T disappears, right? We cancel out a T. 0 divided by T, T divided by T, T squared divided by T. Now what do we do at that time? One word answer. What do we do at that time? Nothing. What were we looking for? Nope. What were we looking for? Time. We're done. Now, if we were looking for the horizontal distance, then what would we do? We take that time and we put it back into here and solve for the displacement, right? We don't need to do that in this question, though. We could, but we don't need to, right? Okay, give these two questions a whirl here, and let's see what we can do with them, okay? Sorry, give this one question a whirl and see what you can do with it. Don't do question number 2, please. Just question number 1. First thing we think of here, 5 words. 5 words. What are they? Yeah. I don't like funny angles, so let's get rid of the funny angle. Let's do it over here on the right-hand side. Here's my 20 meters per second. Here's my 60 degrees. This is the x side of that triangle. This is the y side. Cosine 60 degrees is equal to x, the adjacent side over the hypotenuse. X ends up being equal to 10 meters per second. Sine 60 degrees, is that right? I think so, yeah. Sine 60 degrees is equal to the opposite side over the hypotenuse. Y ends up being equal to 17.33 meters per second. I had lots of people ask me as you guys are working on these questions, oh, is that my answer? I'm looking for this horizontal distance. Isn't this my answer? No, it's not. What have I just found right there with 10 meters per second? Not my horizontal displacement, rather, Zach, my horizontal velocity, right? So I'm not done. I'm going to use that, but I'm not done yet. Yep. X and Y are supposed to be switched. No, cos is adjacent over hypotenuse. Yeah. Yeah. Yeah, I've forgotten those two sometimes, right? So I mean, I use them so much now that I don't forget them, but, you know, I have forgotten them. Just, you know, you ever get confused with that? Just write down SOHCAHTOA, because that's the way you guys have learned it, right? SOHCAHTOA. And that reminds you which is which then. Okay. All right. So let's go back here now and do x and y components. The x component, always described by the same equation every single time. The y component, almost always described by this one. V for the x component. Oh, we know this one, right? Tyler, what's V for the x component? No, but you're close. Not 17. V for the x component. Good. 10 meters per second. Delta D for the x component, don't know. Delta T, don't know. Okay, not helpful. Not yet, anyways. Delta D, Bryant, for the y component. Yep, 0. Good. Lands at the level it started at, right? VI for the y component. Leo, what's VI for the y component? No. No. The other one. VI for the y component. Right, you got it. 17.33. Now, one of the t's cancels, right? Okay, if we divide everything by t, we end up getting 0 is equal to 17.33. Subtract 4.905 times t. Take it to the other side. And we solve for time. 3.5, 3.534. 3.534 seconds, which we're going to turn around and plug into here. We multiply 10 by 3.534, and we get a displacement of 35 meters. Just going to round it to 2 digits. 35 meters. Good? That's not so bad, eh? I got a question for you, though. What if this question had asked you, not for how far the ball traveled, but what if the question had asked you for, what's the maximum height? Maybe you're inside a building and you want to see if it hits the roof or not. What would you do? Well, there's a couple things you could do. One way is easier, okay, than the other. Here's the easiest way. Analyze the y component again. Analyze the y component again. But this time for the y component, let's use this equation. Vf squared is equal to Vi squared plus 2AD. All right. This time for the y component, we're not analyzing the entire trip. We're analyzing half the trip, right? Right up to here. For the y component, listen very carefully. For the y component here, Vf at the top will be 0. It's still moving. The ball is still moving, but not up and down. When it reaches the top, it's not moving up and down anymore. It's moving only horizontally at the top. So if we're analyzing the y component, what's Vf for the y component when I reach the top? 0. Vi for the y component is 17.33. Square that. There we go. Solve for delta D. We just said the speed at the top is 0. What's the displacement at the top? That's the max height. That's what we're looking for in this case. So let's rearrange this. Let's get 17.33 squared. $300.3289 minus 4.905 D, because that's 2 times 9. No, wait. 2 times 9.81 isn't 4.905, right? 2 seconds, guys. Just 2 seconds. Let's finish this. Negative 19.62 times D. Take it to the other side. Don't pack up yet, please. Let's divide that by 19. And we get a max height of 15 meters. So we had to do something different for the max height, right? Okay. I'll tell you right now, question number 1 on that exam was a projectile motion question where you're going to be asked to find how far it goes. You're also going to be asked to find the maximum height of the object. Okay? Here's your homework for tonight. There's a little worksheet that I'm going to hand out to you. I want you to do, there's 2 sides to it with a number of questions on each side. I want you to do number 1 to 3 on both sides. So don't do 4 and 5 on either side. Just do 1 to 3 on both sides, please. That's it for today.